Hi guys, welcome to this lesson where it's going to be an extension of lesson 7.5. So it's really not in your book, so I couldn't really label it like we normally do. But instead of talking about 2D vectors like we did in the last lesson, we're going to talk about 3D vectors. And a lot of it is going to overlap with 2D vectors. And then in the last lesson, we talked about dot products. And so we are going to extend it to cross products because cross products only deal, it's like dot products in concept, but it's going to deal with 3D vectors. So before we really get started, I want to talk about like what does a point in 3 dimensions look like? And so I have this diagram here. Sometimes it looks a little bit different, but you'll get the idea. So like, think about our classroom where we have like the floor and then we have like 2 different walls coming together. So that point at which like all 3 of them meet are right there. So kind of picture that in your head. I think that will help. So we have this x-axis. So like for example, this point 1, 2, 3. So this x-axis is going to go 1 out on the x-axis. So it's kind of going this way. If you can picture, I'm terrible drawer, you guys know this. And then the y is going to meet up. This looks terrible. So think about this, like we're on the floor. And what we have to do, so we have 1, 2 on the floor. So we're used to this. It just looks super weird now. It's just a regular like X, Y. It would be on the floor of our classroom. Then we have to go up to 3. So this looks, so you're probably asking me, well, this looks like it's at like -4. It's not. Like it's on the floor and then you're going to go up 3, like the height. So if somebody was standing on the floor at 1, 3, you know, or I'm sorry, 1, 2, then we would go up 3 from there. So hopefully that makes sense. I'm not going to test you on that or anything. I just wanted you to kind of see how that works. Okay, everything that I'm going to do here is no different than 2D. So this is really nice. So remember in 2D, when we added the vectors, we just literally added their components together. So for this one, let me erase this. This one's going to be 1, and then -2 plus 1 is -1. 4 plus 7 is 11. For 2v, 2 times the vector v, remember we just multiply everything by 2. So 2, -4, and 8. For this is kind of interesting because in 2D, we treated it because of like Pythagorean theorem, we're going to continue on that same process. So instead of saying like a, square root of a squared plus b squared, we're going to add plus c squared as well. So we're focusing on this v. So I'm going to say 1 squared plus technically -2 squared, but 2 squared because I don't care about the negative, and then plus 4 squared. And let's see, 16, 20, 21, so square root of 21. So remember, magnitude means length, so that's going to be the length of our vector. So kind of get that pictured in your head. Okay, so now we're going to find the dot product. So remember how you find dot product. You are just multiplying these 2, multiplying these 2, multiplying these 2, and then adding everything together. So let's go ahead and do that. So 1 times 0, that's 0, plus, let's clear off this mess here, -2 times 1, that's -2. And then we have 4 times 7, which is 28. So our dot product is 26. And then if you'll recall, we use a dot product to find the angle between the 2 vectors. So we have these 2 vectors. So if we could like plot them, which I have a hard time plotting them, obviously. So I'm not going to make you do it. We're just going to go through the process. You're comfortable with the process of it. So the angle between the 2 vectors, what we're going to do is we're going to put the dot product on top, and then it's the magnitudes of the 2 vectors on bottom being multiplied together. So the magnitude of v times the magnitude of u. And that is going to be equal to the cosine of theta. So hopefully that sounds familiar to you from the 2D space. Okay, so we already have the magnitude of v, so go ahead and find the magnitude of u. Okay, so remember, I don't really care about simplifying that or rationalizing the denominator. We are doing basically I'll show you, the cosine inverse of this yuckiness here. So go ahead and type that into your calculator and see what you get. Okay, and if you type it in your calculator correctly, you should get about 36.64 degrees. And so that is the angle between the two vectors. So again, I have not taught you anything new. We're just applying it to 3D vectors. Okay, guys, we are skipping this part and we are going to go down to this. So we haven't had these exact directions, but these exact directions show up on your test. So let me kind of break this down. We have had this. So in 7.4, we talked about a unit vector. So remember, if we get it down to the unit vector, that brought us in the unit circle. And so we could do different things. Same concept applies. So if you remember, what we did is we took each component and we divided it by the magnitude of that vector. So I'm going to do this every single time. I can't write small enough, but you guys get the idea. I'm going to take each of those components and divide by the magnitude. So first of all, we have to find the magnitude. So we have 4 plus 1 plus 1 square root of 6. So the unit vector is simply going to be 2 over the square root of 6, 1 over the square root of 6, and negative 1 over the square root of 6. So I don't like it as messy. I am going to rationalize it first, and then I think I can even simplify it more. Yeah, so this one is going to be square root of 6 over 3, square root of 6 over 6, and negative square root of 6 over 6. So this is the unit vector in the direction V. So basically all you're doing, I just wanted you to be clear on the directions because I think this is kind of weird, but basically all you're doing is finding that unit vector that technically is in the same direction as your original vector. And so you're going to see this on your test in 2D as well. So just know that you're finding the unit vector. That's all you're doing. Okay, so for this next example, we're going to talk about the position vector. We had this also in 2D space. So we were trying to find vector PQ. And so what I told you to do is take Q minus P. And we're going to do the same thing. So 2 minus negative 1 is 3. And another way to look at it, it's just really common sense. Like, just think about like how far have you moved in the X position. So we've gone from negative 1 to 2, so we've moved 3 spaces. We've moved from 4 to 3, so we've moved negative 1 space. And 5 to negative 1, we've moved negative 6 spaces. So either way you want to look at it, like if you are a formula person, that's definitely it. But you can also kind of common sense your way through this one too. Okay, guys, we are going to kind of take this, pick apart this diagram, and it's really hard to picture. So just do what you can. Worst case scenario, you just can't wrap your mind around this. You just follow the procedures and you'll get to where you need to go. So we have this 3D diagram. So remember the corner of our classroom that I talked about? That's right there. That's our origin. So we have this vector V coming out from that origin. And so remember how if you have like 2 intersecting lines, they form a plane. So this plane is formed between like X and vector V and Y and vector V and Z and vector V. So the X, this is called, we're going to talk about directional angles. Sorry, let me write that down. Directional angles. Okay, so the directional angle that is formed between X and the vector is this angle alpha. Okay, the directional angle that is formed between Y and the vector V is this angle beta. And likewise, the directional angle that's formed between the Z axis and vector V is this directional angle gamma. So in order to find those three angles, we are going to follow these three formulas. So again, this is alpha, beta, and gamma. This is probably a new one to you. So in 2D space, we saw the I and the J unit vectors. Now we have the K unit vector. And notice like in 2D space, it was a combination of like cosine I and sine J. Well, now this is just like completely different. So it's all cosine. So like, please do not get it mixed up with the 2D directional angles, like the resultant vectors that we talked about. This is like a completely different formula. Also, something else to know is that these angles will always be between 0 and 180 degrees. Okay, so let's do this example. Find the directional angles of V equals negative 3I plus 2J minus 6K. So think about directional angles, what they're asking. They're asking for like these angles. So the first thing that we're going to do is we're going to find the magnitude. So remember, think about this is just the vector negative 3, 2, and negative 6. So we're going to find the magnitude of that, which you can totally do. And it comes out as a nice answer 7. So this will make our answers really nice. So let's come up here. So let's apply this formula to this problem. Okay, so this is our next step. So we're just going to do like cosine inverse on everything and solve for each of the alpha, beta, and gamma. So go ahead and do that. Okay, so let's go back and refer to the diagram. So this angle here was about 115.4 degrees. This angle here was 73.4-ish degrees, and this angle here was 148.997 degrees. So that's what we're finding there, those directional angles.